Hello everyone. Today I'm going to be discussing Chapter 12 on problem solving. First, note that some of the assignment due dates are different this week than previous weeks. So make sure that you check the syllabus and Canvas for the due dates of this week's assignments. Also, because this week is shorter than most weeks, I'm not going to be covering as much new information on these PowerPoint slides. Instead, I'm going to be mostly using them to clarify some of the more difficult terms from the chapters. So first, these are the main problems described in Chapter 12, so make sure you have tried to solve these problems before viewing the PowerPoint. For the quizzes and exams, I'll expect you to be generally familiar with them and to know the concept that they demonstrate, but I won't test you directly on the nitty-gritty details. In other words, I expect you to know what concept about problem solving the candle and two-string problems demonstrate, but I won't ask you in a short answer question to describe how the problems go. So let's begin by defining the term problem, which is when an obstacle exists between a present state and a goal state, and the solution is not immediately obvious. When I teach this section in my face-to-face class, I begin by asking students to tell me some problems that they've solved recently, and I hear things like math problems, figuring out how to turn your assignments in on time, relationship problems, figuring out whether I want to go to graduate school when I graduate from FSU, problems with finding a job, things like that. All of those are good examples of problems. There's an obstacle between the person's present state and their goal state where they want to end up, and the solution isn't immediately obvious. So figuring out how to open a locked door when you have a key in your pocket wouldn't be a problem, because although there is an obstacle, there is a locked door you need to get through, the solution is very obvious. You use your key in your pocket. We can divide problems into two broad categories, the first being well-defined problems, which are problems with one correct answer that the right procedure will uncover. A good example of well-defined problems are math problems. You probably had to solve problems like 8x equals 45 minus 3x in high school algebra courses. Well, there's only one correct answer for the value of x, and if you use the right procedure, if you put all the x values on one side of the equation and solve for x, you'd be able to determine the correct answer. The other types of problems are ill-defined problems, which are problems with no correct answer, with no clear path for solving. These would be problems like, should I break up with my significant other? Where should I work once I graduate? Problems like those. Again, there's no one correct answer to these problems like there was for the well-defined algebra problem, and there's not necessarily a right or wrong way to go about solving these problems. We'll begin by discussing the Gestalt approach to problem solving, where they viewed success in problem solving as depending on reorganizing or restructuring the problem into a solvable representation. The circle problem is a good example of this, which is for you to find the length of the segment marked x if the radius of the circle is r. So how does one go about finding the length of x? Well, one way to describe this problem is a circle with vertical and horizontal lines that divide the circle into quarters with a small triangle in the upper left quadrant. However, the key to solving this problem is to change how this problem is represented. That is to change the description to a circle with vertical and horizontal lines that divide the circle into quadrants with a small rectangle in the upper left quadrant, with x being the diagonal between the corners. The idea is once you view that shape as a rectangle, you can see that x is the length of one of its diagonals. We can then add the second diagonal, and simple geometry tells us that the length of these diagonals must be the same. Well, what is the diagonal in green? That's also the radius of the circle, which is r. So to answer the question, the length of x is r, the radius of the circle. To reiterate, we solved the circle problem by restructuring the problem to view the shape as a rectangle and not a triangle, and by doing so we can see that x equals r. And this is how the Gestalt perspective conceptualizes problem solving by restructuring the problem into a solvable representation. Now, a lot of the problems that Gestalt psychologists studied were known as insight problems, problems where the solution is discovered with a single moment of clarity. That is, it seemed to participants like they would be thinking about these types of problems for a while, and then like all of a sudden they would come up with the answer in a flash of insight. The triangle problem is a good example of an insight problem. In the triangle problem, you have a triangle formed by 10 dots that is pointing up. Your task is to change the position of 3 of those dots to get the triangle to point down. Now, there's no formula or equation you can use to solve this problem, and you might try some guesses that turn out to be wrong. But if you think about it for a while, eventually you might come up with the answer: to take these three dots and to put them here to get the triangle to point downwards. So again, this isn't like an algebra problem, which would be an example of a non-insight problem, where as you progress through the formula, you get closer to solving the problem. Instead, with insight problems like this triangle problem, the solution is discovered all at once in a single moment of insight or clarity. And the textbook discusses how there is evidence to suggest that insight problems are solved differently than non-insight problems like algebra problems. Specifically, when solving an insight problem, people report feeling far from identifying the solution right up to the point that they solve it. The graph shows participants' warmth ratings for 15-second intervals leading up to the time when they solved the problem. That is, they had to rate on a scale from 0 to 7 how close they felt they were to solving the problem. For insight problems, as indicated by the red line, the warmth rating stayed low until the last 15 seconds when they jumped up suddenly. That is, people felt like they were far from solving the insight problems until right before they did so. On the other hand, for non-insight problems like algebra problems, people report gradually feeling like they're approaching a solution. So in the graph, the blue line, representing non-insight problems, gradually rises as people get closer and closer to solving the problem. That is, participants' warmth ratings gradually increase as they feel like they're continuously getting closer to solving the problem. Next, the textbook talks about two obstacles to problem solving, the first of which is demonstrated by the candle problem. The candle problem is that you have these materials, a matchbox with matches in it, candles and thumbtacks, and your task is to mount the candle on a corkboard so that the candle will burn without dripping wax on the floor. The solution to the problem is to use the tacks to pin the box to the wall and then place the candle on top of the box. But in studies, many participants don't come up with this solution. The reason they have trouble coming up with this solution, specifically using the matchbox as a candle holder, is something known as functional fixedness, which is that knowledge of an object's function can inhibit its use for a different function. The idea is that matchboxes are typically used as containers to hold matches. That's their normal function, not to provide support to other objects. And so it doesn't occur to participants to use them for a different function. That's functional fixedness. Again, knowledge of an object's function can inhibit its use for a different function. Now, functional fixedness can be alleviated somewhat in this example if you give participants these supplies with the matches outside of the matchbox. When you do so, the argument is that participants are less likely to view the matchbox simply as a container for holding the matches, and so participants are more likely to consider consider other uses for it. We can see, for instance, that when the matches are placed outside the box's empty condition, that participants are more likely to solve the problem than when the matches are in the box, where the box is seen as a container condition. Another obstacle to problem solving described in the textbook is illustrated by the water jug problem. In this problem, participants are given 3 jugs, A, B, and C, each of which can hold different amounts of water. They are told that they need to end up with a certain desired quantity of cups of water in one of those jugs. So for problem 1, they need to end up with 100 cups of water in jug B. So how does one solve this problem? Well, the solution is to fill up jug B with water and then to use jug B to fill jug A. When you do that, you're left with 106 cups of water in jug B. So to put this mathematically, the first step is jug B minus jug A. The next step is to fill up jug C with water from jug B, and then to dump the water out of jug C and fill it up with water from jug B again. Or again, to put it more mathematically, jug B minus 2 jug C. When you do that, you're left with 100 cups of water in jug B, the desired quantity for problem number 1. Next, participants are given 7 more problems to solve, and the key point is all of these problems can be solved with the same solution: jug B minus jug A minus 2 jug C. So why is this problem interesting? Well, the water jug problem and the way people normally solve it demonstrate something known as a mental set, which is a person's tendency to respond, that is to solve problems, in the same way as in the past, even when other solutions are easier. I mentioned on the previous slide that participants had to solve 8 total problems, all of which could be solved using the jug B minus jug A minus 2 jug C formula. However, if you look closely at the last two problems, they have an easier solution. For number 7, you can fill jug A and jug C up with water and pour both into jug B. And for number 8, you can fill jug A up with water and pour A into jug C, leaving you with the desired quantity in jug A. Again, both of these problems can be solved using the old, more complex solution of jug B minus jug A minus 2 jug C, but they also have a new, easier solution. The interesting finding is that participants who solved the previous 6 problems using the normal, long solution, in other words, those who developed a mental set, continued to use that solution when solving problems 7 and 8. That is, many of them didn't see the easier solution. However, for participants who started with problems 7 and 8 and then solved the rest, those who never developed a mental set, all of them used the easier solution. So again, this problem demonstrates the concept of mental set. Solving the first 6 problems using the same longer solution causes participants to use this same long solution on problems 7 and 8, even though an easier one is available. The last thing I want to do today is to discuss the modern approach to problem solving by going over Newell and Simon's model and to contrast it with the Gestalt approach. Remember, according to the Gestalt approach, the way problems are solved is to restructure or reorganize the problem into a more solvable solution. But the basis of the modern perspective on problem solving is that one has to consider the intermediate states between the problem and the solution, as well as the rules one has to follow to solve the problem. The reason for this difference in perspective is not that people think the Gestalt approach is wrong per se, but that the types of problem solving it was meant to describe, those insight problems, were fairly simple and could be solved in one step. On the other hand, other types of problems are more complicated and can't be solved in one step. And so this approach is about describing how more complex problems are solved. First, let me introduce some terminology, and note that for the exam, I want you to be able to define and recognize examples of these terms, as well as to be able to apply them to the Tower of Hanoi problem, which I'll discuss in a minute. So the first 2 terms are initial state and goal state. The initial state is the conditions at the beginning of the problem, and the goal state refers to the conditions at the end of the problem. So again, these refer to the conditions in the problem when it is presented, and the conditions in the problem when it is solved, respectively. Next are the intermediate states, which are the conditions that exist along the pathway between the initial state and the goal state. So remember, for most problems, you can't go directly from the problem as it is presented to the solution in just one step. You have to take it along intermediate states. This is what's new about this perspective to problem solving, describing how the problem is progressed through these states. And finally, operators are the rules or moves that can be made to solve the problem, to bring it from the initial state to the goal state. So again, the operators are rules in solving problems. As an example I give in my face-to-face class to further demonstrate these terms, let's think about grilling a hamburger. Its initial state is a frozen lump of meat, and its goal state is a nicely grilled patty that is ready to be eaten. The point is, though, that you can't go directly from the frozen hunk of meat to the grilled patty in just one step. The meat has to go through intermediate states instead. For instance, first the meat has to be defrosted, then it has to be shaped into hamburger patties, and then you have to grill one side and then flip it to grill the other side, at which point you finally arrive at the goal state. So all of those would reflect the intermediate states of the hamburger. Finally, the operators would be the rules for grilling. Keep the patties to about 1/4 pound each, preheat the grill, don't burn the meat, things like that. So now that you hopefully have a general idea about what these terms mean, let's apply them to the Tower of Hanoi problem. So here we see the initial state and the goal state of the problem. The initial state, where the disks begin, is on the left peg, ordered from the smallest disk on top to the largest disk on the bottom, and then the goal state, where you want the disks to end up, is on the right peg in order from the smallest disk on top to the largest disk on the bottom. Now, you can't just move all 3 disks at once because of the operators or rules of the problem, which are the following. Rule 1 is that you can move 1 disk at a time from one peg to another. Rule 2 is that you can only move a disk when there are no disks above it. And rule 3 is that a larger disk can never be placed on top of a smaller disk. And so, how do you get the disks from the initial state to the goal state if you can't move all of them at once? Well, the answer is you have to go through the intermediate states. Now, these are all of the possible intermediate states in the Tower of Hanoi problem. The fastest way of solving the problem is depicted on the far right pathway, but as you can see, again, there are many possible moves to make. In other words, there are many places the pegs can be in between them being initially on the left peg and ending up on the right peg in order. The question is then, how does one solve this problem, or how do you figure out which is the next correct move to make? Well, what Newell and Simon say is that you perform a means-end analysis, which involves solving the problem by reducing the difference between the current state and the goal state. So like we've been saying, in the Tower of Hanoi problem, you start with all three disks on the left peg, and you want to get them to the right peg. The first thing you need to do to reduce this difference is to move the top small disk so you can get at the larger disks below it. Because remember, the bottom disk on the right peg has to be the largest disk. Specifically, Newell and Simon say performing this means-end analysis leads to the creation of subgoals, which are methods of creating intermediate states that are closer to the goal state. In other words, you solve the problem by completing each of its subgoals. So beginning with the problem's initial state, where all three disks are on the left peg, the first subgoal is to free up the large disk by moving the small and medium disks to different pegs. Now that we have this as our intermediate state, we'll perform our means-end analysis again and ask ourselves, what can we do to reduce the difference between this current state and the goal state? Well, to get to the goal state, we need to move the disks to the right peg, so our next sub-goal is to free up the third peg, the right peg. And finally, the bottom disk on the third peg has to be the large one, so our third sub-goal is to move the large disk onto the third right peg. Again, notice by completing each of these sub-goals, we're creating an intermediate state that is closer to the goal state. Okay, that's all I have for this PowerPoint. As always, please post any questions you have in the discussion board.